Hello. Today we are going to do a few questions which are from the textbook, and the very first one we're going to pick up is to find or to write or find the HCF using the division algorithm. So as we had studied in the previous slides or the videos, that we first find out the HCF by the division method. So you have 135, and that's dividing 2 to 5. We divided by 1 times, so it's 135. Now this is 0 and this is 9 over here. Now we divide the previous divisor by the remainder, so 135, and so 1s are 90, so we are left with 45. Now once again we divide the previous divisor by the remainder, and this is 45, 2s are 90. Now we shall write the division algorithm. We shall start with 225. That can be written as 135 times 1 plus 90. Then we shall write 135 is equal to 90 times 1 plus 45, and then we have 90, which is equal to 45 times 2 plus 0, and so 45 is the HCF. In a similar way, we shall go on to find the HCF for 196 and 38220. So we start the same way. 196, we have 38220. First it goes one time, so it's 196. We are left with 186. We bring down 2. Now if it will be say 9, so 9 6 are 54. Okay, so 9 6 are 54, 9 9s are 81, and 5 is 86. 9 was a 9 and 8 is 17. Now this is equal to 12 minus 5 is 7, and 15 minus 6 is 9. 90, 9 6 are 54. We have committed a mistake here. Okay, so this is 9 6 are 54, then 6, and then 17, and that leaves us with 98, and we divide, so this will be 190, just a minute, 98, and then the 0 and a 0, then 196 into 5 6 are 30, 9 5 are 45, 48, so 5 6 are 30, 9 5 are 45, 48, and 9. So we are not left with any remainder. So over here we can write 38220 as 196 into 195 plus 0. So because the divisor was 196, 196 is the HCF. Okay, now coming on to the Euclid's division algorithm to show that any positive odd integer is of the form 6q plus 1, 6q plus 3, or 6q plus 5. Now over here we can see that the divisor is 6. So according to the remainder theorem, also the remainder should be either 0, 1, 2, 3, 4, 5, or 6. So we shall write any integer is of the form 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. But out of all these, here 6q can be written as 2 times 3 into q. 6q plus 2 can be written as 2 times 3q plus 1. and 6q plus 4 can be written as 2 times 3q plus 2. Now because these three, 6q, 6q plus 2 and 6q plus 4 are all multiples of 2, and therefore 6q, 6q plus 2 and 6q plus 4 are even, and therefore 6q plus 1, 6q plus 3 and 6q plus 5 are odd, and therefore we can say any positive odd integer is of the form six q plus 1, 6q plus 3 or 6q plus 5. Now, talking about the other question, to use Euclid's division lemma to show that the square of any positive integer is of the form 3m plus 1. So what do we do is we start with any positive odd integer, or say any positive integer, any positive integer is of the form 3m plus 1, or let us take it as q so that we end up with m at the end, 3q plus 1 or 3q plus 2, because the remainder should be less than 3. Now over here it says the square, so if n is equal to 3q, that implies n square is equal to 9q square, which can be written as 3 times 3q square. And if we consider, because it is 3 times something, so we will write 3 times m. So where m represents an integer which is 3q square as far as this particular question is concerned. Basically the idea is that whatever you square, it should either end up with 3m or 3m plus 1. Now we look at the second integer, which is n, which is equal to 3q plus 1. So that implies n square is equal to 3q plus 1 the whole square, which makes it 9q square plus 6q plus 1. Now if I take out 3 common from the first two, I get 3q square plus 2q plus 1. Now see, over here we know that we can also take out q common, but there is no need. Now the first part, which is 3 into 3q square plus 2q, that means it's a multiple of 3, so we again write it as 3 times m plus 1, where m again represents some integer. So basically it means it is 3 times the integer which is equal to 3q square plus 2q. And then we go on to write n is equal to 3q plus 2, which implies n square is equal to 3q plus 2 the whole square, which is 9q square plus 12q plus 4. Now we can further break it up as 9q square plus 12q plus 3 plus 1 is equal to 3 common, 3q square plus 4q plus 1 plus 1, and then once again we get 3m plus 1. And therefore any positive integer, the square of any positive integer is of the form 3m or 3m plus 1. 3m or 3m plus 1. Okay, now let's talk about the second one. Use the Euclid's division lemma to show that the cube of any positive integer. So let's begin by taking that any positive integer is of the form 3m, 3m plus 1 and 3m plus 2. Now for n is equal to 3m, it implies n cube is equal to 27m cube, which is equal to 3 times 9m cube. Now let us consider it as m, so it is 3 cube. Or if you want, you may start with 3 cube. Just a minute, because we have to answer the final answer as 3 cube plus 1. So let it be 3 cube plus 1 and 3 cube plus 2. So if n is equal to 3 cube, it implies n cube is equal to 27q cube, which is 3 times 9q cube, which is equal to 9 times m. We need to keep 9 outside. Now if we talk about n is equal to 3 cube plus 1, it implies n cube is equal to 3 cube plus 1 the whole cube. Now we apply the formula of a plus b the whole cube. So we have a cube plus 3a square b. So that's 27q plus 3ab square is 9q and plus bq. Now we get 9 common from the first 3. So it is 3q cube plus 3q square plus q plus 1. And this results into 9m plus 1. And once again, n is equal to 3 cube plus 2, which gives n cube is equal to 3 cube plus 2 the whole cube. That's once again a cube plus 3a square b. So 27 2s are 54q square plus 3ab square. So 6 is a 9 for the 36q, and plus 2 to the 4 2s are 8. And this is equal to, you get 9 common from the first 3, 3q cube plus 6q square plus 4q plus 8. And that is equal to 9m plus 8. And so the cube of any positive integer is of the form 9m plus 1 or 9m plus 8.